started with a dot, a single pixel on a screen. Nothing more. July 12th, 2024, 2:47 a.m. The Atlas telescope in Hawaii was doing what it does every night. Scanning the sky, photographing stars, looking for anything that moves. Asteroids, comets, space rocks drifting through the dark. The system is automated. No one was watching in real time. The algorithm flagged it first. A moving object. Faint. Fast. Too fast. When the astronomer on duty saw the alert that morning, he almost dismissed it. False positives happen all the time. Satellites, glitches, cosmic rays hitting the camera sensor. But this one was different. It wasn't in orbit around Earth. It wasn't following the sun. It was cutting through the solar system at a speed that didn't make sense. 137 kilometers per second. Let that sink in. That's over 300,000 miles per hour. Faster than any comet we've ever tracked. Faster than anything natural should be moving unless it came from somewhere else. And it did. Within hours, the discovery was confirmed by telescopes in Chile, South Africa, and Arizona. Every observation pointed to the same conclusion. This object wasn't born here. It came from outside, from the space between stars. They gave it a name, 3I Atlas. The I stands for interstellar. The third confirmed visitor from beyond our solar system in all of human history. The first was Oumuamua, discovered in 2017. Cigar-shaped, strange, gone before we could study it properly. The second was Borisov in 2019. A comet, familiar, almost boring by comparison. But this one? 3I Atlas was different from the start. News of the discovery spread through the astronomy community like wildfire. Within 24 hours, telescopes on 6 continents were being redirected. Observation schedules were cleared. Research teams scrambled to get viewing time. This wasn't just another space rock. This was a visitor. A traveler from another star system, crossing through our cosmic neighborhood. And everyone wanted to see it. Dr. Sarah Chen was among the first to lock onto it. She works at the European Southern Observatory in Chile, operating one of the most powerful telescopes on Earth. When the alert came through, she and her team immediately began tracking. We expected it to behave like Borisov, she said in an interview months later. A dirty snowball, tumbling, chaotic. That's what comets do. She paused, choosing her words carefully. But from the very first night, something felt different. The first thing that struck astronomers was the speed. 137 kilometers per second is fast. To put that in perspective, the fastest human-made object ever, the Parker Solar Probe, tops out at about 163 kilometers per second, and that's only when it's diving close to the sun, using gravity to slingshot itself forward. 3I Atlas was maintaining that speed naturally. No engine, no fuel, just raw velocity carried from wherever it came from. But speed alone wasn't what made it unusual. It was the trajectory. When something enters our solar system from interstellar space, it usually comes in at a steep angle. Think of the solar system as a flat dinner plate, with the sun in the middle and the planets orbiting in a thin disk around it. That disk is called the ecliptic plane. Most interstellar objects come from above or below that plane, cutting through at random angles. Because space is three-dimensional, because they're coming from random directions in the galaxy. But 3I Atlas, it arrived almost flat with the ecliptic, tilted only 5 degrees, nearly aligned with the plane of our planets. Dr. Marcus Delgado, an orbital mechanics expert at the Lowell Observatory in Arizona, ran the numbers. The probability of an interstellar object arriving at such a shallow angle is about 1 in 500, he explained. Not impossible, but noteworthy. He pulled up a simulation on his screen, showing the object's path cutting through the solar system like a blade. It's coming in clean, almost too clean. As July turned to August, more data started coming in, and that's when things got weird. Comets are messy. They tumble as they move. They vent gas unevenly. They wobble. When you point a telescope at a comet and measure its brightness over time, what astronomers call a light curve, you get chaos, spikes, dips, randomness. Because the object is irregular, spinning unpredictably, reflecting sunlight in every direction. But when Dr. Chen's team measured 3I Atlas, the light curve was smooth. Too smooth. I thought our instruments were malfunctioning, she admitted. We recalibrated, ran diagnostics, but the pattern held. Every 11 hours and 42 minutes, the object's brightness would rise, then fall, in a perfect rhythm. Not random, not chaotic, periodic, like clockwork. Dr. Chen shared the data with colleagues around the world. Within days, observatories in Japan, Australia, and Hawaii confirmed the same thing. A repeating cycle, 11.7 hours. Every time, no deviation. Natural objects don't do that, said Dr. Delgado, his voice measured but firm. I've studied rotating asteroids for 2 decades. They wobble, they precess, their spin rates change. He zoomed in on the light curve data. This is the kind of stability you see in satellites, in spacecraft. He stopped himself. I'm not saying it is a spacecraft, but this level of precision, it's unusual. The email started. Quiet at first, between colleagues, private conversations, and academic forums. Has anyone else noticed the periodicity? This rotation model doesn't make sense. We should talk, not over email. By late August, the whispers were getting louder. Avi Loeb, the Harvard physicist who'd famously suggested Oumuamua might be artificial, published a preprint paper. The title was careful, academic, but the message was clear. 3I Atlas displays characteristics inconsistent with standard cometary models and warrants further investigation. In the conclusion, he wrote, "We cannot yet prove this. Object is natural, and until we can, we should treat it as an open question." The response was immediate. Some called it bold, necessary, others called it reckless. "This is how you destroy credibility," one prominent astronomer tweeted, jumping to conclusions based on incomplete data. But Loeb didn't back down. "I'm not jumping to conclusions," he replied. "I'm refusing to dismiss possibilities before we have evidence." The media picked it up. Headlines ranged from cautious to sensational. New interstellar object shows unusual spin. Is 3I Atlas more than a comet? Scientists suggest visitor could be probe. The public was fascinated. YouTube videos dissecting the discovery racked up millions of views. Reddit threads exploded with theories. Twitter debates raged. Everyone had an opinion. But in the observatories, in the quiet rooms where data is analyzed and careers are built, the scientists kept watching. Because the object was getting closer. And the data? It kept getting stranger. One detail began to stand out. 3I Atlas wasn't just passing through the solar system. Its trajectory was bringing it close to multiple planets: Mars, Venus, Jupiter, and Earth. Dr. Delgado mapped it out. The object would pass within 18 million miles of Mars in October, then swing by Venus in early November, then approach Earth in December. The closest any confirmed interstellar object had ever come to our planet. Finally, it would pass near Jupiter in early 2025. 4 planets, 1 path. Each pass individually could be coincidence, Delgado said. But together? He shook his head. The combined probability of threading this trajectory, hitting all 4 encounter windows, is about 1 in 20,000. He let that sink in. That's not impossible, but it's improbable. And then there was the timing. 3I Atlas was headed toward perihelion, the closest point to the sun, on October 29th. This is the moment astronomers wait for. When solar heat is at maximum, when the object's true composition is revealed, when everything becomes clear. But on October 29th, Earth would be on the exact opposite side of the sun, solar conjunction. The object would be hidden, eclipsed by the star it was passing. For 3 weeks, no telescope on Earth would be able to see it. Dr. Chen stared at the orbital projection. "That's unfortunate timing," she said quietly. But her colleague sitting beside her didn't look convinced. "Is it?" As September gave way to October, 3I Atlas continued its approach. The rhythm never stopped, the trajectory never wavered, and the questions kept piling up. What was this thing? Where did it come from? And why did it feel like it was coming toward us? In observatories around the world, astronomers prepared for perihelion. They knew they'd lose sight of the object for 3 weeks. They knew the most critical moment would happen in darkness. But they hoped, desperately, that when 3I Atlas reemerged, it would finally make sense. It didn't. September 2024. By now, 3I Atlas had become the most watched object in the solar system, not just by professional astronomers, by everyone. Amateur astrophotographers were capturing images from their backyards. Students were tracking it in university observatories. Citizen scientists were downloading public data and running their own analyses. The object had captured the world's imagination. But for the professionals, the ones with access to humanity's most powerful telescopes, something else was happening. They were starting to see things that didn't make sense. Dr. Yuki Tanaka had been tracking 3I Atlas since mid-August from the Subaru telescope in Hawaii. Her job was straightforward: measure the object's brightness over time and build what's called a light curve. For a comet, this is routine work. You point your telescope. You measure how much light reflects back. You record it. Over days and weeks, you build a graph showing how brightness changes. Most comets look like chaos on a graph. The brightness jumps around, spikes high, drops low, Flickers unpredictably. Because comets tumble. They're irregularly shaped chunks of ice and rocks spinning through space. As they rotate, different parts catch the sunlight. Some surfaces are bright, others are dark. Some are covered in fresh ice. Others are dusty and dull. So the light curve bounces. Chaotic. Random. That's what Dr. Tanaka expected when she started tracking 3I Atlas. That's not what she got. On September 3rd, after 2 weeks of continuous observation, she sat in her office staring at her monitor. The graph on her screen showed a perfect wave, rising, falling, rising again, like a sine wave in a physics textbook. Every peak was the same height, every valley the same depth. The spacing between them, exactly 11 hours and 42 minutes. No variation, no drift, no noise. She rubbed her eyes, checked the calibration logs, reran the data processing pipeline. The pattern held. She picked up her phone and called her supervisor. We need to talk about this object. Within 24 hours, teams around the world were seeing the same thing. The Gemini Observatory in Chile, the Keck telescopes in Hawaii, the European Southern Observatory, NASA's Hubble Space Telescope orbiting high above Earth's atmosphere. All of them recorded the same rhythm, the same pattern. 11.7 hours. Repeating. Forever. Dr. Marcus Delgado was blunt when asked about it during a virtual conference in mid-September. I've been studying asteroids and comets for 23 years, he said, his face filling the Zoom screen. I have never seen rotational stability like this in a natural object. He shared his screen, showing comparison graphs. On the left, light curves from known comets. Messy, irregular, chaotic. On the right, 3I Atlas, a perfect repeating wave. This is the kind of precision you see in engineered systems. Satellites maintain stable rotation through gyroscopes and thrusters. But a comet? He shook his head. Comets get hit by radiation pressure, by micrometeoroids, by their own outgassing. All of that creates torque. It changes the spin. Natural objects wobble. He pointed at the graph. This one doesn't wobble. Someone in the chat asked the question everyone was thinking. Could it be artificial? Delgado was silent for a moment. I'm saying the data is inconsistent with what we know about natural rotation. That's all I can say. But his eyes said more. The scientific community was fracturing. In public statements and press releases, most astronomers stuck to careful language. Unusual but explainable. Requires further study. Likely a natural phenomenon we haven't encountered before. But in private, the conversations were different. Email threads with subject lines like re-3I periodicity, your thoughts, were flying between institutions. Slack channels buzzed with speculation. Late-night calls between colleagues stretched for hours. One email, later leaked to a science journalism blog, simply read, "At what point do we stop pretending this is normal?" Dr. Sarah Chen tried to stay measured. She'd built her career on careful analysis, on not jumping to conclusions, but even she was struggling. In early September, her team at the European Southern Observatory had been running spectroscopic analysis on 3I Atlas, breaking down the light from the object to see what it was made of. Comets have signatures. Water ice shows up as specific absorption lines in the spectrum. Carbon dioxide, methane, organic compounds. 3I Atlas showed all the expected signatures: water, CO2, dust. But there was something else. Something that made her stop and rerun the analysis 3 times. Nickel vapor. Not just nickel. That would be unusual but not impossible. Some comets release trace metals when they heat up. But this wasn't trace amounts. This was 4.6 grams per second of nickel being released into space. And it wasn't just nickel atoms. It was nickel tetracarbonyl. Dr. Chen called in a chemistry consultant from Caltech. Dr. Amara Okonkwo arrived on a video call looking skeptical. She'd seen plenty of false positives in her career. Bad data, contamination, instrumental artifacts. But when Chen showed her the spectral lines, Okonkwo went quiet. "That's nickel tetracarbonyl," she said slowly. "I know." "From a comet?" "That's what the data says." Okonkwo leaned back in her chair. "Dr. Chen, nickel tetracarbonyl doesn't exist in nature. It's a synthetic compound. It forms under very specific industrial conditions. High pressure, carbon monoxide atmosphere, metal catalysts. Could it form in space, in some unusual environment?" Okonkwo thought for a long time. "I suppose, theoretically, if you had a very strange protoplanetary disk with bizarre chemistry, maybe. But I've never seen it proposed in any formation model, and I've certainly never seen it detected." She looked at the data again. "Where did you say this object came from?" "Outside the solar system." "Right, and it's moving how fast?" 137 kilometers per second. Okonkwo was quiet. Then, "You know what this looks like, right?" Chen nodded. It looks like industrial exhaust. The two women sat in silence. Finally, Okonkwo spoke. What are you going to do with this? Publish it. The data is solid. You know what people are going to say. I know. Chen published the findings in a preprint paper on September 18th. The title was clinical: Detection of Nickel Tetracarbonyl Emission in Interstellar Object 3I Atlas. The paper was downloaded 50,000 times in the first 48 hours. The comment section exploded. Some researchers praised the rigorous methodology. Others questioned the instruments. A few suggested contamination from Earth's atmosphere, even though 3I Atlas was millions of kilometers away. But no one could explain it away. The compound was there, in the data, undeniable. Meanwhile, NASA's James Webb Space Telescope was conducting its own observations. JWST is the most powerful infrared telescope ever built, capable of seeing details invisible to other instruments. In late September, the Webb team released their analysis of 3I Atlas's thermal signature. Comets are cold. Even when they approach the sun, most of their mass stays frozen. You expect to see a temperature gradient, hotter on the sun-facing side, colder on the night side. But 3I Atlas showed something odd. The temperature distribution was too uniform, as if heat was being distributed evenly across the surface. Not through natural thermal conduction, ice and rock are poor conductors, but through something else. One engineer on the Webb team noted privately, "This looks like active thermal management, like a spacecraft radiating heat evenly to avoid hot spots." That comment never made it into the official report. By early October, the pattern was clear. Every measurement, every observation, every dataset pointed in the same direction. This object was behaving with precision, with regularity, with characteristics that kept brushing up against the edge of what natural processes could explain. The 11.7-hour pulse, the industrial chemistry, the thermal uniformity. Individually, each could be explained away. Maybe, with creative theories and generous assumptions, but together? Avi Loeb published another paper in early October. This one was more direct. "We are observing an object that displays at least 5 anomalous characteristics," he wrote. "At some point, parsimony demands we consider alternatives to the natural explanation." He proposed a framework, a scale from 0 to 10. 0 means definitely natural. 10 means definitely artificial. Most comets rate a 1 or 2. Some unusual asteroids might hit a 3. Loeb rated 3I Atlas at a 6. The paper was controversial, intentionally so. Loeb knew what he was doing. He was forcing the conversation that everyone else was avoiding. "We can't keep pretending every anomaly is just another coincidence," he said in an interview. "At some point, the weight of evidence demands we ask uncomfortable questions." Critics pounced. "This is unscientific speculation. We need extraordinary evidence for extraordinary claims. Loeb is damaging the credibility of serious astronomy." But the public? The public was listening. News outlets picked up the story. Not just science publications, mainstream media, the object that pulses like a machine, the chemistry that shouldn't exist, the Harvard scientists saying it might be artificial. Social media exploded. YouTube videos analyzing the data got millions of views. Reddit threads stretched into thousands of comments. Everyone had an opinion. Some said Loeb was brave for speaking truth. Others said he was an attention seeker. But no one could ignore the data, because the data kept getting stranger. In mid-October, just 2 weeks before perihelion, radio telescopes around the world quietly began monitoring 3I Atlas. SETI, the Search for Extraterrestrial Intelligence, had been watching from the sidelines. Officially, they had no comment on whether the object warranted investigation. Unofficially, they were listening. The Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, smaller arrays scattered across the globe. All of them pointed at 3I Atlas, scanning across radio frequencies, looking for any hint of a signal. They listened for 2 weeks. Nothing. No narrowband transmission, no modulated signal, no carrier wave, just silence. And somehow that silence felt significant. Because if 3I Atlas was artificial, if it was a probe from another civilization, why would it be broadcasting? Maybe it was just observing, gathering data, transmitting back to its origin using methods we couldn't detect. Or maybe it was doing something else entirely. Dr. Tanaka said it best in a late-night conversation with colleagues. "We keep assuming that if it's artificial, it would look like our technology. Radio signals, heat signatures, obvious propulsion." She stared at the light curve on her screen, that perfect, repeating wave. But what if it's not like our technology at all? What if we're looking at something so advanced that we can't even recognize it as artificial? The question hung in the air. As October progressed, 3I Atlas drew closer to the sun. The pulse continued, the chemistry persisted, the thermal signature remained uniform, and on October 29th, the object would reach perihelion. The moment of truth. The moment when solar heat would strip away surface layers and reveal what lay beneath. The moment when all the questions should finally get answers. Except there was a problem. On October 29th, Earth would be on the exact opposite side of the Sun, and no one would be able to see what happened. October 29th, 2024. The date had been circled on calendars and observatories around the world for months. Perihelion, the closest approach to the Sun. For 3i Atlas, that meant 126 million kilometers from our star, just inside the orbit of Mars, deep in the zone where solar radiation is intense enough to vaporize ice, strip away surface layers, and reveal the true composition of whatever lies beneath. This is the moment when comets transform, when dormant ice becomes active gas, when hidden chemistry emerges, when the mask comes off. Astronomers had been waiting for this moment since July. 3 months of watching, measuring, debating. Now finally they would get answers. Except they wouldn't. Because on October 29th, 3i Atlas would pass directly behind the Sun from Earth's perspective. Solar conjunction, perfect alignment. From our vantage point, the object would be hidden, swallowed by the glare of the star it was passing. Every telescope on Earth rendered useless. The timing was, by all accounts, unfortunate. Dr. Sarah Chen stood in the control room at the European Southern Observatory, watching the orbital projection on the main screen. The trajectory line showed 3i Atlas approaching the Sun, arcing behind it, then emerging on the other side 3 weeks later. 3 weeks, 21 days of darkness, right at the most critical moment. Bad luck, one of her colleagues muttered. Chen didn't respond. She was staring at the numbers, at the probabilities. The odds of an interstellar object reaching perihelion at the exact moment Earth happened to be on the opposite side of the Sun? About 1 in 25. Not impossible. Space is full of coincidences. But combined with everything else, the pulse, the chemistry, the trajectory threading past multiple planets, this was another improbability added to the pile. And the pile was getting tall. Dr. Marcus Delgado was more direct. In a video interview published October 15th, 2 weeks before perihelion, he was asked about the timing. "Look," he said, choosing his words carefully. "I'm not saying this is intentional, but if I were designing a spacecraft and I wanted to make course corrections without being observed..." He trailed off. The interviewer pressed. "You're saying it could maneuver behind the Sun?" "I'm saying we won't be able to see what it does. That's just geometry. But yes, if there were ever a moment to change trajectory without detection, this would be it." He pulled up a diagram. "There's a concept in orbital mechanics called the Oberth effect. When you're moving fast near a massive object, like the Sun, even a small thrust produces a huge change in your final trajectory. You're essentially amplifying your engine's power using gravity and velocity. So perihelion is the optimal place for a maneuver?" "Exactly. Maximum speed, maximum gravity, maximum efficiency. And maximum invisibility." Delgado nodded slowly. "And maximum invisibility." The interview went viral. Within hours, it had been shared across every major platform: YouTube, Twitter, Reddit, TikTok. The public was riveted. The idea that something might be happening behind the Sun, hidden from view, at the exact moment we should be watching most closely, it was the perfect setup for mystery. But in the scientific community, the reaction was more divided. Some researchers supported Delgado's caution. "We should be open to possibilities, and us and us," they argued. "That's literally what science is." Others were furious. "This is irresponsible speculation." One prominent astronomer tweeted, "We're supposed to follow evidence, not conspiracy theories." Avi Loeb predictably sided with Delgado. "The fact that we can't observe the object during its most critical phase is significant," he wrote. "Whether by design or coincidence, we now have a gap in our data, and that gap matters." He continued, "In science, we often learn as much from what we can't see as from what we can. The absence of observation is itself a data point. But not everyone could just sit and wait." NASA's Stereo mission, 2 spacecraft that orbit the Sun at different positions, giving us multiple viewpoints, was still operational, though aging. One of the spacecraft, Stereo A, would have a partial line of sight to 3i Atlas during the blackout period. Not perfect, the angle was oblique, the resolution would be poor, but it was something. On October 20th, NASA quietly redirected Stereo A's cameras toward the projected position of 3i Atlas. They didn't announce it publicly, no press release, no fanfare. Just a technical observation campaign filed in the mission logs. October 29th arrived. Around the world, astronomers watched their screens as 3i Atlas disappeared into solar glare. The last clear images showed a glowing coma, a cloud of gas and dust surrounding the nucleus, with a faint tail streaming away from the Sun. It looked by all accounts like a comet, and then it was gone. For 3 weeks, the object was invisible, hidden behind 1.4 million kilometers of plasma and nuclear fusion. Ground-based telescopes couldn't point anywhere near the Sun without risking damage. Hubble and James Webb had strict safety protocols preventing them from observing too close to solar glare. Even stereo A's view was marginal at best. The data trickled in slowly. Low-resolution images, thermal measurements, spectroscopic readings. Dr. Yuki Tanaka was part of the team analyzing the stereo data in real time. Day after day, she watched the fuzzy images appear on her screen. The object was still there, still glowing, still releasing gas. Nominal comet behavior, the official report stated, but Tanaka noticed something. On October 31st, 2 days after perihelion, the brightness of 3I Atlas dropped. Not gradually, not slowly, suddenly. In a 48-hour window, the object lost nearly 30% of its brightness. Then it stabilized. Tanaka ran the numbers through every outgassing model she had. Comets can fragment near the sun. Pieces can break off, reducing the overall brightness. But fragmentation is violent, chaotic. You see debris clouds. You see asymmetric expansion. This wasn't that. This was a clean drop, sharp, controlled, like something had been released. She shared the data with colleagues, quietly, in encrypted emails. One response came back within an hour. Are we seeing a separation event? The idea was almost too much to consider. What if 3I Atlas hadn't fragmented? What if it had deployed something? A smaller probe, a sensor package, a daughter craft. What if the brightness drop wasn't loss, but release? The speculation stayed private. No one was willing to put it in a paper. Not yet. Not without more evidence. But the seed was planted. As November began, 3I Atlas started to re-emerge from behind the sun, first as a faint glow in Stereo's cameras, then gradually becoming visible to Earth-based telescopes. Observatories around the world immediately locked on. The first priority, recalculate the trajectory. Orbits are sacred in astronomy. You can predict where an object will be years in advance, down to the meter, because gravity is mathematics. If something deviates from its predicted path, there's a reason. The calculations took 3 days, and when they came back, the room went silent. 0.03 degrees. The trajectory had shifted. Not much. In cosmic terms, it was tiny. A fraction of a percent. But it was there. Measurable. Real. Dr. Delgado was the first to publish the analysis. His paper, uploaded November 18th, was clinical and precise. Post-perihelion observations indicate a trajectory deviation of 0.03 degrees relative to pre-perihelion predictions. Analysis suggests non-gravitational acceleration inconsistent with standard outgassing models. In plain English, the object had changed course, and the change was too precise to be random gas jets. The response was immediate. Some scientists argued it could still be outgassing. Maybe a focused jet on one side of the object, venting at just the right moment, pushing it slightly off course. But others weren't convinced. Outgassing is chaotic, Dr. Chen said in a conference call. You get multiple jets firing in different directions. They push and pull. You see wobble, you see drift. She pulled up the data. This is clean. One direction, one vector, no secondary effects. Someone asked the question everyone was thinking. So what does that mean? Chen took a breath. It means we're looking at either the most statistically unlikely series of coincidences in observational astronomy, or something else. Something else hung in the air like smoke. Because there was another detail, one that made the trajectory shift even more interesting. The new path wasn't random, it was pointing toward Jupiter. If 3I Atlas continued on this course, it would pass within 54 million kilometers of the gas giant in early 2025. Close enough for a gravitational assist. Close enough to slingshot around and gain even more velocity. Or change direction again. Dr. Delgado plotted it out. If this object uses Jupiter for a gravity assist, it could alter its trajectory significantly, maybe even enough to stay in the solar system longer, or leave at a completely different angle than it arrived. He stared at the projection. But here's the thing. To set up a Jupiter encounter from perihelion, you need precision. You need to know where Jupiter will be months in advance. You need to aim. Someone in the back of the room said what everyone was thinking. Natural objects don't aim. The media caught the trajectory shift within 24 hours. Headlines screamed, "Interstellar object changes course after passing sun, and did 3I Atlas just maneuver?" The public reaction was explosive. Conspiracy theories bloomed overnight. Some claimed it was proof of alien technology. Others said scientists were overreacting, seeing patterns in noise. But in the labs, the debates were more nuanced. Was this a maneuver, or an unusual outgassing event? Was the timing coincidence, or navigation? Was 3I Atlas a comet, or something pretending to be one? Dr. Chen sent an email to her team November 20th. It was meant to be internal, private. It leaked within 48 hours. The email read, "We are now tracking an object that 1. Pulses with mechanical regularity, 2 emits industrial chemicals, 3 passed behind the sun at the optimal moment for unobserved maneuvering, 4 shifted trajectory with unusual precision, and 5 is now on course for a Jupiter encounter. At what point do we stop calling this coincidence? The leak caused an uproar. Some accused her of abandoning scientific rigor, of giving in to sensationalism. Others thanked her for saying what needed to be said, but no one could dispute the facts. The data was the data. And as November gave way to December, one thing became clear. 3I Atlas was now on a path that would bring it closer to Earth than any confirmed interstellar object in history. 170 million kilometers, not close by everyday standards, but close enough. Close enough to study in unprecedented detail, close enough finally to get answers, or so everyone hoped. Because deep down in the minds of the scientists tracking this object across the sky, a new question was forming. Not what is it, but what does it want? Act 4. The Chemistry of Machines. December 3rd, 2024. The Very Large Telescope in Chile had been tracking 3I Atlas for weeks, but tonight was different. Tonight they were hunting for something specific. Dr. Sarah Chen stood in the control room at the Paranal Observatory, watching the spectroscopic data stream across her monitor in real time. Around her, 3 other researchers sat in silence, their eyes fixed on their own screens. Spectroscopy is one of the most powerful tools in astronomy. It works by splitting light into its component colors, like a prism turning sunlight into a rainbow. But instead of just pretty colors, astronomers see something far more valuable: chemical signatures. Every element, every molecule absorbs and emits light at specific wavelengths. Sodium creates 2 bright yellow lines. Hydrogen produces a series of red and blue lines. Water vapor shows up as clusters of absorption bands in the infrared. It's like a fingerprint, unique, unmistakable. When you point a spectrograph at a comet, you expect to see certain fingerprints: water ice, carbon dioxide, methane, ammonia. Simple organic compounds, the basic ingredients of the early solar system, frozen and preserved. That's what Chen expected when she started the observation run 3 hours ago. That's not what she was seeing now. "Run it again," she said quietly. Her colleague, Dr. Andreas Müller, didn't argue. He'd already run the calibration twice, but he did it again anyway. The data didn't change. There, clear as day in the spectrum, was a series of lines that didn't belong. Nickel carbonyl, specifically nickel tetracarbonyl, NiCO 4. Chen stared at the screen. Her heart was beating faster than she wanted to admit. "How much?" she asked. Müller ran the calculations. Based on the emission strength, approximately 4.6 grams per second. 4.6 grams doesn't sound like much. A teaspoon of sugar weighs more. But this wasn't sugar. And it wasn't just sitting there. This was 4.6 grams per second being released continuously into space, hour after hour, day after day. That meant tons of the compound venting from the surface of 3I Atlas. Chen pulled up the reference database. Every known spectral signature ever recorded from comets, asteroids, planetary atmospheres, stellar atmospheres, interstellar clouds. Nickel tetracarbonyl appeared exactly once, in laboratory spectra, taken on Earth, in industrial settings, never in space. "Check for iron," she said. "Because nickel and iron always appear together. They're forged in the same supernova explosions. They travel through space together. They condense together in planetary systems. Finding nickel without iron is like finding smoke without fire." Müller scanned the spectrum. Once, twice, 3 times. "Nothing," he said. "No iron lines at all." The room went very quiet. Chen stood up and walked to the window. Outside, the Chilean desert stretched for miles under a sky so clear you could see the Milky Way as a river of light. Somewhere up there, 3I Atlas was racing through the solar system, venting a chemical compound that had no business existing outside a factory. She pulled out her phone and started typing an email. The subject line: "We need to talk about the chemistry." By December 5th, the news had spread through the astronomical community like wildfire. Not publicly, not yet, but in private channels, encrypted emails, late-night video calls, the word was out. 3I Atlas was emitting nickel tetracarbonyl. Dr. Amara Okonkwo, the chemistry consultant from Caltech, had been following the spectroscopic data for months. When Chen sent her the new findings, she spent 2 days reviewing every possible natural explanation. Then she published a technical analysis on a preprint server. The paper was dense. 43 pages of chemical modeling, thermodynamic calculations, and formation scenarios. The conclusion was 3 sentences long. Nickel tetracarbonyl does not form under any known natural astrophysical conditions. Its presence in 3I Atlas requires either exotic chemistry beyond current theoretical models or a non-natural source. Further investigation is urgently warranted. In academic language, that was about as close to screaming as you could get. The paper was downloaded 80,000 times in the first week. Dr. Marcus Delgado read it twice. Then he called Chen. "Tell me I'm misunderstanding this," he said. "You're not. Nickel tetracarbonyl is synthetic." "Yes." "It requires industrial processes." "Yes." "High pressure. Carbon monoxide atmosphere. Metal catalysts." "That's what the literature says." Delgado was quiet for a long moment. "Sarah, do you understand what you're implying?" "I'm not implying anything. I'm reporting what we detected." "The media is going to have a field day with this." Chen sighed. "I know." And they did. The story broke on December 10th when a science journalist got hold of Okonkwo's preprint. The headline, "Interstellar Comet Emits Industrial Chemical Found Only in Factories." Within hours, it was everywhere. News websites, YouTube, Twitter, Reddit, TikTok. The reactions were immediate and polarized. Some people saw it as definitive proof of alien technology. "Finally," they said. "Finally, real evidence." Others dismissed it as hype. "Scientists are misinterpreting the data," they argued. There has to be a natural explanation. But in the middle were millions of people who simply didn't know what to think. Because the chemistry was real, the compound was there, and no one could explain it. Dr. Yuki Tanaka from the Subaru telescope tried to stay measured during a press interview. "What we're seeing is unprecedented," she said carefully. "But unprecedented doesn't automatically mean artificial. It means we're encountering chemistry we haven't seen before." The interviewer pressed. "But nickel tetracarbonyl is only made in factories, correct?" "On Earth, yes. But space is vast. There could be formation environments we haven't considered." "Like what?" Tanaka hesitated. "We're working on several hypotheses." But privately, she was struggling to find any that held up. One theory proposed that 3I Atlas had formed in a protoplanetary disk around a carbon-rich star, where unusual chemistry might allow nickel compounds to form without iron. The problem? Even in the most exotic stellar environments, iron is abundant. You can't selectively remove it. The nuclear physics doesn't work that way. Another theory suggested the compound might be trapped in subsurface ice, preserved from some ancient chemical process billions of years ago. The problem? Nickel tetracarbonyl is unstable. It breaks down over time, especially under radiation. It wouldn't survive billions of years frozen in ice. A third theory proposed contamination. Maybe Earth's atmosphere had somehow tainted the measurements. Problem? 3I Atlas was 150 million kilometers away. No Earth-based contamination could reach it, and multiple independent observatories had confirmed the detection. Every natural explanation required special pleading. Exotic conditions, unlikely scenarios, convenient exceptions to known chemistry. The simplest explanation was the one no one wanted to say out loud. This compound was being manufactured. Avi Loeb had no such hesitation. On December 12th, he published an op-ed in Scientific American titled, "When Simple Explanations Become Uncomfortable." In Science, he wrote, "We follow Occam's razor. The simplest explanation is usually correct, but there's a corollary that often gets ignored. The simplest explanation is only simple if we're willing to consider all possibilities." He continued, "Nickel tetracarbonyl is a synthetic compound. On Earth, we make it in factories through specific industrial processes. When we detect it coming from an interstellar object, the simplest explanation is that it's being produced by similar processes. The only reason this explanation seems complicated is because it requires accepting that we're not alone in the universe. But that's a philosophical discomfort, not a scientific one." The response was immediate and fierce. Dr. Linda Zhao from MIT fired back in a blog post. "Loeb is conflating simple with sensational. The simplest explanation is that we're observing rare natural chemistry, not that aliens are flying through our solar system in a factory ship." Others piled on. "Extraordinary claims require extraordinary evidence. We can't abandon natural explanations just because they're difficult. This is irresponsible speculation." But Loeb didn't back down. In an interview, he put it simply, "I'm not claiming 3I Atlas is artificial. I'm claiming we should investigate it as if it might be, because if we're wrong, we've wasted some telescope time. But if we're right and we ignore it, we've missed the most important discovery in human history." Meanwhile, the chemistry kept getting stranger. On December 15th, the James Webb Space Telescope completed a detailed infrared spectroscopic analysis of 3I Atlas. The data showed not just nickel tetracarbonyl, but a whole suite of compounds. Carbon monoxide, carbon dioxide, water vapor, cyanide, all expected from a comet. But the ratios were wrong. Most comets are dominated by water ice. It makes up 70–80% of the volatile material. Carbon dioxide is usually a distant second, maybe 10–15%. 3I Atlas was inverted. Carbon dioxide was 8 times more abundant than water. Dr. Chen ran the numbers through every formation model she could find. Comets that form far from their parent star in the coldest regions can have higher CO2 ratios. But 8 to 1? That was extreme. It's like this thing formed at the edge of interstellar space, she told her team. Or, she didn't finish the sentence, but everyone knew what she was thinking. Or it's not ice at all, it's propellant. Carbon dioxide is stable, easy to store, easy to release in controlled jets. If you were designing a spacecraft for interstellar travel, you might use CO2 as a reaction mass. Heat it up, let it expand, use it for minor course corrections. From a distance, it would look exactly like a comet. The speculation was swirling now, impossible to contain. On December 18th, a Reddit user with a background in chemical engineering posted a detailed analysis. Let's assume for a moment that 3I Atlas is artificial, the post began. What would its chemistry tell us? The post laid out a scenario. You're building a probe for interstellar travel. You need it to survive for millions of years. You need protection from radiation, from impacts, from the cold of deep space. So you coat it in ice, regular water ice with some CO2 mixed in. Its insulation, its shielding, its camouflage. But you also need fuel for minor adjustments, so you store compressed CO2 in tanks. When you need to maneuver, you heat it and vent it. From the outside, it looks like natural outgassing. Now your hull is made of metal alloys, advanced materials, and as you travel through space, cosmic rays bombard the surface. Some of those metals, nickel specifically, get vaporized. They react with the CO you're venting and form nickel tetracarbonyl. It's not intentional, it's just a byproduct of the chemistry happening on your hull. The post concluded, the chemistry we're seeing isn't proof of technology, but it's exactly what we'd expect if technology were present. The post went viral. Millions of views, thousands of comments. News outlets picked it up. Scientists were divided on how to respond. Some called it creative speculation with no scientific basis. Others said quietly, "It's not wrong." Dr. Okonkwo was asked about it in an interview. "Is that scenario plausible?" the interviewer asked. She chose her words carefully. The chemistry described is accurate. If you had a metallic surface being irradiated in space and you were venting carbon monoxide, you could produce nickel tetracarbonyl as a byproduct. So it's possible? It's chemically consistent. Whether it's what's actually happening, that's a different question. But her eyes said more than her words. By late December, the chemical data had been confirmed by 5 independent observatories. Nickel tetracarbonyl, present. Iron, absent. CO2 to H2O ratio, 8 to 1. Emission rate, steady, not variable. Every data point was a small anomaly. Every anomaly had a possible natural explanation. But together they formed a pattern that looked less like random comet chemistry and more like industrial exhaust. Dr. Chen summarized it in a year-end review paper. The chemical composition of 3I Atlas challenges our understanding of natural cometary processes. While exotic formation scenarios cannot be ruled out, the observed compounds and ratios are inconsistent with standard models of planetary system chemistry. It was the most cautious way possible to say, this doesn't make sense. And as the year came to a close, as 3I Atlas continued its journey through the solar system, one question hung in the air. If the chemistry was this strange, what else were we missing? December 20th, 2024. Dr. Marcus Delgado hadn't slept properly in 3 days. He sat in his office at the Lowell Observatory, surrounded by printouts of orbital calculations, coffee cups, and increasingly frantic notes scrawled on a whiteboard. For the past month, he'd been working on something that should have been straightforward, calculating the mass of 3I Atlas. In astronomy, you can't just put an object on a scale. You have to infer mass from behavior. The most common method uses gravity. If an object passes near a planet, the planet pulls on it, and the object pulls back. By measuring how much the object's path bends, you can calculate its mass. But 3I Atlas hadn't passed close enough to any planet for that method to work. So Delgado was using a different technique, non-gravitational acceleration. When comets vent gas, that gas acts like a tiny rocket engine. It pushes the comet, changes its trajectory. The amount of push depends on 2 things, how much gas is being released and how massive the comet is. If you know the gas production rate, which multiple telescopes had measured, and you measure the trajectory change, which orbital tracking provided, you can calculate the mass. It's basic physics. Force equals mass. Times acceleration. Solve for mass. Delgado had run the calculation 17 times. Every time he got the same answer, and every time it made less sense. 33 billion tons. Minimum. He stared at the number on his screen. For context, the Great Pyramid of Giza weighs about 6 million tons. 3I Atlas weighed as much as 5,500 pyramids. It was massive, far more massive than it should be. The previous interstellar visitors, Oumuamua and Borisov, had been small. Oumuamua was maybe 200 meters across, probably weighing a few million tons. Borisov was slightly larger, maybe a kilometer wide. 3I Atlas was in a completely different category. Based on its brightness and reflectivity, astronomers estimated it was somewhere between 5 and 10 kilometers in diameter. If it were a solid chunk of ice and rock, like a normal comet, with a density around 0.5 to 0.9 grams per cubic centimeter, you'd expect it to weigh... Delgado did the math again. Between 30 and 40 billion tons, so the mass calculation matched. The object was exactly as heavy as it should be if it were solid, except for one problem. It was venting gas. Lots of gas. The James Webb Space Telescope had measured the outflow rate on August 6th, approximately 150 kilograms per second. That's a third of a ton every second streaming off the surface and into space. When gas vents from one side of a comet, it pushes the comet in the opposite direction. It's Newton's third law, action and reaction. This push is called non-gravitational acceleration, and it's measurable. Every comet ever observed shows it. The object speeds up or slows down or shifts sideways as gas jets fire unpredictably from its surface. But 3I Atlas, its trajectory matched a purely gravitational path to within 0.01%. The upper limit on its non-gravitational acceleration was less than 0.001 meters per second squared. That's effectively zero. Which meant one of two things. Either the gas was venting perfectly symmetrically from all sides, canceling out all the forces, which was statistically impossible for a rotating, irregularly shaped comet, or the object was so massive that the thrust from the gas couldn't move it. Like trying to push a cruise ship with a hairdryer. The force exists, but the mass is too large for the effect to be measurable. Delgado leaned back in his chair and closed his eyes. If 3I Atlas were solid, 33 billion tons of ice and rock, then yes, the gas jets wouldn't move it much. But here's the thing about solid objects that massive. They're rare. Based on models of planetary formation, the odds of a 10-kilometer object being ejected from a star system and wandering through interstellar space are tiny. We should see hundreds of smaller objects before we see one this big. But 3I Atlas was only the third interstellar visitor we'd ever detected. The odds didn't add up. Unless... Delgado opened his eyes and stared at the whiteboard. Unless it wasn't solid. He picked up a marker and started sketching. A sphere. 10 kilometers across. Now instead of drawing it solid, he drew it as a shell. A hollow sphere with walls a few hundred meters thick. The interior, empty space. He ran the numbers. A hollow sphere 10 kilometers in diameter, with walls 200 meters thick, made of metal or advanced composite materials, would weigh approximately 33 billion tons. Exactly what the data showed. And a hollow structure would explain everything. The mass? Check. The numbers matched perfectly. The lack of non-gravitational acceleration? Check. The outgassing was coming from ice coating the outside of the shell, not from the internal structure. The shell itself was too massive to be pushed by surface jets. The thermal signature? Check. A hollow sphere with active thermal management could distribute heat evenly, avoiding hotspots. Delgado sat very still. He was looking at a model that explained every anomaly. But it was a model that required accepting something extraordinary. Because natural processes don't create hollow spheres 10 kilometers across. Nature makes solid objects, lumpy, irregular, dense. Hollow structures are engineering. He saved the calculations and sent them to 3 colleagues he trusted. The subject line: "Please check my math, urgently." Within 6 hours, all 3 had responded. The math was correct. Dr. Sarah Chen called him. "Marcus, are you really suggesting this thing is hollow?" "I'm suggesting the data is consistent with a hollow structure." "That's the same thing." "No, it's not. I'm following the evidence. The evidence says massive, but not affected by outgassing. Hollow explains that." "It also implies artificial construction." Delgado was quiet. Then, "Yes, it does." Chen let out a long breath. "What do we do with this?" "We publish. Let the community evaluate it." "You know what's going to happen." "I know." On December 23rd, Delgado submitted his paper to the Astrophysical Journal. The title: Mass Determination of 3I Atlas via Non-Gravitational Acceleration Limits. Implications for Internal Structure. The abstract was carefully worded, clinical, precise, but the conclusion was unavoidable. The observed mass and lack of detectable non-gravitational acceleration are most readily explained by a hollow or internally differentiated structure inconsistent with standard cometary models. The paper went through peer review faster than any submission in the journal's history. 3 reviewers, all with the same response. The math is sound. The conclusion is radical. Publish and let the field debate it. It appeared online December 28th. The internet exploded. Scientist claims interstellar object may be hollow. Is 3I Atlas an alien spacecraft? New study suggests comet could be artificial structure. Within 24 hours, the paper had been downloaded 200,000 times. Dr. Yuki Tanaka read it carefully. Then she ran her own calculations. The numbers held. She called a colleague in Japan. If this is right, she said slowly, we're not looking at a comet. We're looking at a shell, a container. Containing what? I don't know, empty space maybe, or something else. The colleague was quiet. This is going to change everything, isn't it? It already has. Avi Loeb had been waiting for something like this. On December 30th, he published a preprint paper that sent shockwaves through the scientific community. The title, Bayesian Analysis of Anomalous Characteristics in Interstellar Object 3I Atlas. In it, he compiled every anomaly. 1. The 11.7-hour mechanical pulse. 2. The nickel tetracarbonyl emissions. 3. The inverted CO2-H2O ratio. 4. The trajectory shift at perihelion 5. The threading path past multiple planets. 6. The thermal uniformity. 7. The hollow structure implied by mass calculations. For each anomaly, he calculated the probability of it occurring naturally. Then he multiplied them together. The result, approximately 1 in 847,000. But that wasn't the controversial part. The controversial part was the conclusion. Using Bayesian probability, a statistical method for updating beliefs based on evidence, Loeb calculated the likelihood that 3I Atlas was artificial versus natural. His conclusion, 30-40% probability of non-natural origin. Not certainty, not proof, but a probability high enough to warrant serious investigation. We have reached the point, he wrote, where the hypothesis of artificial origin can no longer be dismissed as speculative. The cumulative weight of anomalous observations demands we consider it as a viable scientific possibility. The response was immediate and divided. Dr. Linda Zhao from MIT published a rebuttal within hours. Loeb is stacking improbabilities dishonestly, she argued. Each anomaly has possible natural explanations. Just because they're unlikely doesn't mean we should jump to aliens. Others agreed. This is sensationalism dressed up as science. We need direct evidence, not statistical games. But some researchers quietly supported Loeb. He's right that we're dismissing possibilities too quickly, one astronomer said anonymously. We're so afraid of being wrong about aliens that we're refusing to look at the data honestly. Another. If this were any other field, if we saw this many anomalies in particle physics or biology, we'd be investigating intensely. But because it touches on extraterrestrial intelligence, we're paralyzed. The media predictably ran with the story. Harvard scientist, 40% chance interstellar object is alien probe. Is 3I Atlas a hollow spacecraft? The comet that might not be a comet. Public opinion was split. Some people were convinced. Finally, someone's telling the truth. Others were skeptical. Scientists are reading too much into normal data. And millions were simply confused, caught between dueling headlines and conflicting expert opinions. Dr. Chen tried to stay balanced in interviews. What we're seeing is genuinely unusual, she said. But unusual doesn't automatically mean artificial. Space is strange. We're constantly encountering things we've never seen before. But the hollow structure is one possible interpretation of the mass data, not the only one. What are the other interpretations? Chen hesitated. We're working on them. But privately, she was struggling. Every natural explanation required special circumstances, unlikely formations, rare chemistry, convenient alignments. The artificial hypothesis, by contrast, explained everything with one assumption: intentional design. It was Occam's razor in reverse. The natural explanation had become the complicated one. On New Year's Eve, Dr. Delgado sat in his office watching the sun set over the Arizona desert. 3I Atlas was out there somewhere, 180 million kilometers away, racing toward its encounter with Jupiter. In a few weeks, it would pass close to the gas giant, close enough for a gravitational assist, close enough to change course again. And if it did, if the trajectory shifted one more time with precision that couldn't be explained by random outgassing, then the debate would be over. Because hollow structures don't navigate, but spacecraft do. Delgado pulled up the orbital projection on his screen. The trajectory line extended forward, curving around Jupiter, then bending outward toward the edge of the solar system. If nothing changed, 3I Atlas would leave our neighborhood by mid-2025, disappearing back into the darkness between stars, taking all its secrets with it. He stared at the screen for a long time. Then he typed an email. 2. Chen, Sarah, Tanaka, Yuki, Loeb, Avi. Subject: observation campaign for Jupiter encounter. We need every telescope we can get pointed at this thing when it passes Jupiter. If it maneuvers again, I want the data to be undeniable. He hit send. Outside, the stars were beginning to appear. Somewhere among them, 3i Atlas continued its journey. Massive, hollow, venting industrial chemicals, moving with purpose through our solar system. And no one, not the skeptics, not the believers, not even the most careful scientists, could say for certain what it was. Only what it wasn't. It wasn't normal. And with each passing day, it was looking less and less like an accident. January 12th, 2025. 240 million kilometers from Earth, a spacecraft the size of a small bus adjusted its orientation in the thin Martian atmosphere. The Mars Reconnaissance Orbiter, MRO for short, had been circling the red planet since 2006, photographing canyons and craters, searching for signs of ancient water, mapping the surface in exquisite detail. But today it had a different target. 3i Atlas was passing Mars at a distance of 29 million kilometers. Not close by everyday standards, still about 75 times farther than the Moon is from Earth, but close enough. Close enough for HiRISE, the high-resolution imaging science experiment. A camera so powerful it could photograph individual boulders on Mars from orbit. A camera designed to capture details smaller than a meter across. Pointing it at something 29 million kilometers away was unconventional. The engineers had never tested it at such extreme range, but the geometry was perfect. The opportunity was unique, and NASA wanted answers. The observation window was narrow, just 4 hours when 3i Atlas would be in the right position, when Mars was between Earth and the object, when the lighting was optimal. At 1422 UTC, HiRISE began capturing images. Frame after frame, different exposures, different filters, different wavelengths. The data was transmitted to Earth over the next 48 hours, beamed across the solar system at the speed of light, arriving at the Deep Space Network stations in California and Australia. By January 15th, the raw images were being processed at the Lunar and Planetary Lab in Tucson, Arizona. Dr. Jennifer Castellano was part of the team analyzing them. She'd spent 15 years studying Mars, ancient riverbeds, polar ice caps, the geology of a dead world, but for 2 weeks her entire focus was on something that had never touched Mars, something passing by. The first processed image appeared on her screen at 3 a.m. on January 16th. She'd been expecting a blur, maybe a faint smudge. HiRISE wasn't designed for this kind of observation. What she got was better than she'd hoped. The image showed a diffuse, roughly circular glow. The coma, the cloud of gas and dust surrounding the nucleus. And in the center, brighter, was an elongated shape, the nucleus itself. Not a perfect sphere, not a clean geometric shape, but irregular, oblong, maybe 8 to 10 kilometers across at its widest point, exactly what you'd expect from a comet. Castellano felt something inside her relax. Despite all the speculation, all the headlines, all the debate, it looked normal. She saved the image and started writing her preliminary report. HiRISE imaging of 3i Atlas shows morphology consistent with natural cometary structure. Nucleus appears elongated, possibly indicating binary contact pair or irregular rotation. Coma symmetric and diffuse, no geometric features detected. She sent it to her supervisor and went to get coffee. When she came back, there was a reply waiting. Check the brightness distribution. Something's off in frame 23. Castellano pulled up frame 23. It was one of the longer exposures, capturing fainter details. She adjusted the contrast, enhanced the brightness levels, and then she saw it. The coma wasn't centered on the nucleus. The brightest region, the densest concentration of gas and dust, was offset, shifted toward the sun-facing side by approximately 50 kilometers. At first, she thought it was measurement error, or an artifact of the imaging process. But she checked frame 24. Same offset. Frame 25. Still there. She ran a photometric analysis, measuring the light distribution across the entire image. The peak brightness was definitely not at the nucleus. It was outside it. Castellano sat back in her chair. In a normal comet, outgassing comes from the surface of the nucleus. Ice sublimates, turns directly from solid to gas, and erupts into space. The densest part of the coma should be right at the source, at the nucleus itself. From there, the gas and dust spread outward, getting thinner and more diffuse with distance. You might see jets, focused streams of material erupting from specific active regions, but the overall brightness distribution should be centered on the solid body. This wasn't. This was like seeing smoke rising from a point 50 kilometers above a fire. She ran simulations. Maybe the nucleus had a large active region on one side, venting so strongly it created an asymmetric distribution. The models didn't match. The offset was too large. Too clean. Maybe the nucleus was fragmented, maybe there were two objects orbiting each other, and the secondary piece was doing most of the outgassing. But the shape didn't support that. The nucleus looked like one elongated body, not two separate pieces. She tried a different approach. What if the nucleus was surrounded by a shell of loosely bound material? Not a solid outer layer, but a cloud of large particles, boulders, chunks of ice floating in formation around the core. If that shell was doing the outgassing, instead of the core, the model worked, sort of. It explained the offset, but it raised a different question. Why would a comet have a shell structure? Castellano wrote it up carefully in her report. Brightness distribution shows offset of approximately 50 plus 5 kilometers from nucleus center. This may indicate asymmetric outgassing, fragmentation, or structural differentiation not immediately apparent in images. Further analysis recommended. She submitted it on January 18th. NASA reviewed it, conferred with imaging specialists, ran their own analysis. On January 24th, they released the images publicly. The press release was straightforward. Mars Reconnaissance Orbiter successfully images interstellar object 3I Atlas. The images were included. High resolution, detailed, beautiful. The description: images showed diffuse coma surrounding elongated nucleus, consistent with cometary structure. Object appears stable with no signs of fragmentation or unusual activity. No mention of the brightness offset, no discussion of the asymmetry. Just consistent with cometary structure. The media ran with it. NASA images confirm 3I Atlas is a comet. Interstellar visitor photographed by Mars orbiter. Looks normal. Scientists, no signs of artificial structure in close-up images. For many people, that was the end of the story. NASA said it was a comet. Case closed. But in the astronomy community, questions were already forming. Dr. Marcus Delgado downloaded the raw image data the same day it was released. Within hours, he'd reproduced Castellano's brightness analysis. He called Dr. Sarah Chen. Have you seen the offset? I'm looking at it now. That's not normal outgassing. I know. So why isn't NASA talking about it? Chen was quiet for a moment. Maybe they don't think it's significant. Sarah, the brightest part of the coma is 50 kilometers away from the nucleus. That's significant. Or maybe, Chen said slowly, they think it's explainable but don't want to feed speculation. By hiding data? By not emphasizing anomalies that might have mundane explanations. Delgado wasn't satisfied. What's the mundane explanation? Chen pulled up her own models. If the nucleus is hollow, like your mass calculations suggest, and the outgassing is coming from the outer shell rather than the interior, you'd see exactly this kind of offset. That's not mundane. That's structural confirmation. It's consistent with the hollow hypothesis. It doesn't prove it. But NASA isn't even mentioning it. Chen sighed. No, they're not. The silence from NASA became its own story. On January 28th, a science journalist filed a Freedom of Information Act request asking for all internal communications regarding the high-rise observation of 3I Atlas. NASA's response: request received and under review. A reporter asked during a press briefing whether radio observations had been conducted during the Mars flyby. The spokesperson's response: we don't comment on ongoing research. But is there ongoing research? No comment. Another journalist asked whether NASA had plans to investigate the brightness offset noted by independent researchers. All data has been released to the public. Independent analysis is welcomed. But what's NASA's analysis? Our assessment is consistent with natural cometary activity. The non-answers became a pattern. Every question about radio monitoring, no comment. Every question about the offset, consistent with natural processes. Every question about whether the object warranted special investigation. Standard observation protocols are being followed. Dr. Yuki Tanaka watched the press briefing from her office in Hawaii. When it ended, she pulled up a private message thread with several colleagues. They're stonewalling. One response came back immediately. Or they found nothing and don't want to say we looked and there was no signal because it legitimizes the question. Another. Or they found something and don't know what to do with it. Tanaka stared at that last message for a long time. The problem with silence is that it can mean anything. It can mean there's nothing to report, or it can mean there's too much to report. In early February, a rumor started circulating, unconfirmed, unverifiable, but persistent. The rumor said that SETI, the Search for Extraterrestrial Intelligence, had pointed radio telescopes at 3I Atlas during the Mars encounter, that they'd monitored across hundreds of frequency bands looking for any hint of transmission, and that they'd found something. Not a clear signal, not a message, but an anomaly, a pattern in the radio noise that didn't fit natural sources. The rumor said the data was being analyzed, that it was inconclusive, that it needed more study before anyone would risk their reputation making it public. Dr. Chen tried to verify it. She had contacts at the SETI Institute, friends who would tell her the truth. but when she asked, they were evasive. We conducted observations. Results are being analyzed. Did you detect anything? Analysis is ongoing. That's not an answer. It's the only answer I can give right now. Chen pushed. If you detected something, anything, you'd tell the community, right? Her contact was quiet for a long moment. Sarah, if we detected something ambiguous, something that could be interference or instrumental noise or natural radio emissions, what do you think we should do? Rush to publish and deal with the media circus? Or take our time, verify, and only speak when we're certain? The latter. Then trust that we're doing exactly that. The conversation ended, but Chen was left with more questions than answers, because ambiguous meant there was something, just nothing clear enough to announce. By mid-February, the Mars flyby images had been analyzed by dozens of independent researchers. Most agreed the brightness offset was real, but debated its significance. Some argued it was evidence of a hollow structure, the smoking gun that Delgado's mass calculations had predicted. Others said it could be explained by asymmetric outgassing from an irregularly shaped nucleus. One paper proposed a rubble pile model, a loose collection of fragments held together weakly by gravity, with outgassing occurring from the spaces between the pieces. The data fit all of these models. Sort of. None perfectly, but all plausibly. Dr. Avi Loeb weighed in with an op-ed. The Mars observations add another piece to the puzzle. A hollow shell would produce exactly this kind of offset brightness. Combined with the mass anomaly, the chemistry, the trajectory, each piece fits the picture of something designed rather than naturally formed. Critics fired back. Loeb is cherry-picking data that fits his narrative and ignoring natural explanations. The debate raged on Twitter, in academic journals, in YouTube videos, and late-night arguments in university labs. But one thing was becoming clear. The Mars flyby hadn't settled anything. If anything, it had deepened the mystery. Because now there was another anomaly to explain. Another detail that didn't quite fit. Another data point that made the natural comet explanation just a little bit harder to defend. And underneath it all, there was the silence. NASA's careful non-statements. SETI's evasive answers. The lack of published radio observations. The absence of information became information itself. What were they not saying? What had they seen, or not seen, that they weren't ready to discuss? Dr. Delgado summarized it in a late-night email to Chen and Tanaka. We have images that show structural anomalies. We have chemistry that doesn't make sense. We have mass calculations that suggest hollowness. We have a trajectory that looks navigated. And we have institutions that are being very, very careful about what they say publicly. At some point, the pattern becomes undeniable. Not proof, but probability. How many anomalies do we need before we admit we're looking at something we don't understand? The email was never meant to be public, but it leaked 2 days later. And the question spread across the internet like wildfire. How many anomalies? How much strange data? How many coincidences stacking on coincidences? Before we stop calling it a comet and start calling it something else? The Mars images were supposed to provide clarity. Instead, they provided one more reason to wonder. One more detail that didn't fit. One more piece of the puzzle that belonged to a picture no one wanted to complete. Because completing it meant accepting something extraordinary. And extraordinary meant upending everything we thought we knew about our place in the universe. So the silence continued. Official, institutional, deafening. While 3i Atlas continued its journey, moving with purpose through our solar system, venting industrial chemicals, pulsing with mechanical rhythm, threading past planets with impossible precision, and carrying secrets that seem determined to remain secrets, at least for now. February 8th, 2025. Dr. Lisa Fung sat in her office at the Jet Propulsion Laboratory in Pasadena, California, surrounded by monitors displaying orbital trajectories. As a spacecraft navigation engineer, she spent her career calculating paths through the solar system, sending probes to Mars, plotting flybys of Saturn, guiding rovers to precise landing spots. She understood orbital mechanics at an intuitive level, and what she was looking at now made absolutely no sense. For the past 6 weeks, she'd been part of a team reconstructing the complete trajectory of 3i Atlas, not just where it was going, but where it had been, where it came from, how it arrived, the full picture. They'd compiled data from over 200 observatories, thousands of position measurements, precise timing of when the object crossed specific points in space. Using those measurements, they could trace the trajectory backward and forward with extraordinary accuracy, and what they found was disturbing. Fung pulled up a three-dimensional model of the solar system on her largest monitor. The sun at the center, planets in their orbits, and cutting through it all, a bright red line, the path of 3i Atlas. She zoomed out, showing where the object had come from. The line extended beyond the solar system, back into interstellar space, originating from somewhere in the direction of the constellation Ursa Major. No specific star, just a general direction. It had been traveling for millions of years probably before entering our neighborhood. Then she zoomed in, focusing on the past 8 months. The trajectory threaded through the inner solar system like a needle through cloth. It passed Venus at 0.65 AU on November 3rd, 2024, about 97 million kilometers. It passed Mars at 0.19 AU on October 3rd, 2024, about 29 million kilometers. It would pass Earth at 1.8 AU in late February, about 270 million kilometers, and it would pass Jupiter at 0.36 AU in March, about 54 million kilometers. 4 planets, 1 trajectory. Feng had run the probability calculations a dozen times. The odds of a random interstellar object passing this close to 4 planets in a single trajectory. She'd gotten different numbers depending on her assumptions, but they all clustered around the same order of magnitude. 1 in 20,000. Not impossible, but highly improbable. What made it worse was the timing. The object didn't just pass near the planet's orbital paths, it passed when the planets were near those intersection points. Venus was within 30 degrees of the crossing point when 3I Atlas passed its orbit. Mars was within 15 degrees. Jupiter would be within 20 degrees. For all 3 to be positioned favorably during a single trajectory, Feng had calculated that probability too, about 1 in 150. Multiply that by the trajectory odds, 1 in 3 million. And that wasn't even the strangest part. She rotated the 3D model, viewing the solar system from above. The planets orbit the sun in roughly the same plane, the ecliptic. It's like a flat disk, with everything moving in roughly the same direction. Objects from outside the solar system should come from random angles. Above the plane, below it, sideways, anywhere. The probability of an interstellar object arriving aligned with the ecliptic plane within 5 degrees was about 1 in 500. 3I Atlas had arrived tilted only 5 degrees from the plane, nearly flat, nearly aligned, as if it had intentionally matched the geometry of our solar system. Feng leaned back in her chair and closed her eyes. She was a spacecraft engineer. She knew what navigated trajectories looked like. Every mission she'd worked on, Curiosity, Perseverance, Juno, had paths that were carefully calculated to encounter specific targets at specific times. You don't just point a spacecraft at Mars and hope for the best. You aim for where Mars will be when you arrive. You account for its motion. You thread the needle, and if you want to visit multiple planets, you design a grand tour. You use gravity assists. You chain encounters together. Voyager did it in the 1970s. Cassini did it in the 2000s. It's possible, but it requires planning, calculation, intent. What she was looking at now was a trajectory that visited 4 planets, that arrived aligned with their orbital plane, that passed each one when timing was favorable. Either it was the luckiest random path in the history of astronomy, or it was navigated. She opened her eyes and started writing her report. The analysis was released as a preprint on February 12th. The title: Geometric and Statistical Analysis of Interstellar Object. 3I Atlas, Implications for Trajectory Origin. The abstract was careful, technical, dry. But the conclusion was clear. The observed trajectory displays characteristics more consistent with designed encounters than random passage. While natural explanations cannot be ruled out, the combined geometric and temporal probabilities warrant consideration of alternative hypotheses. In academic language, that was about as close to saying "this looks artificial" as you could get without actually saying it. The paper was downloaded 300,000 times in the first week. Dr. Marcus Delgado read it twice. Then he called Feng. "You're saying it's navigating." "I'm saying the trajectory looks navigated. Whether it is navigated is a different question." "What's the natural explanation?" Feng sighed. "Luck, coincidence, a 1 in 3 million chance that happened to occur." "Do you believe that?" She was quiet for a long moment. "I've spent 15 years calculating spacecraft trajectories. I know what intentional paths look like, and this looks intentional." "But you can't prove it." "No, I can't prove intent. I can only describe geometry." Delgado thought about that. "What would constitute proof?" "Another course correction. If it maneuvers around Jupiter, if it adjusts trajectory one more time with precision, that can't be explained by outgassing, then we're not looking at coincidence anymore. We're looking at navigation." "Yes." The conversation ended, but the implications hung in the air. Because Jupiter was 3 weeks away, and everyone was watching. The media picked up Feng's paper immediately. NASA scientist, interstellar objects path, looks designed. New study shows 3I Atlas trajectory has 1 in 3 million odds. Is the comet following a planned route through the solar system? Public reaction was intense. Some people saw it as confirmation. Finally, someone with credentials is admitting the truth. Others dismissed it. Scientists are finding patterns in randomness, classic pareidolia. But the numbers were hard to argue with. 1 in 20,000 for the planetary encounters, 1 in 500 for the ecliptic alignment, 1 in 25 for the perihelion timing during solar conjunction. Multiply them together and you got probabilities that made people uncomfortable. Dr. Sarah Chen tried to stay balanced in interviews. Statistical improbability doesn't equal impossibility, she said. Unlikely things happen all the time. That's what unlikely means. They're rare, but they occur. But at what point do we stop attributing things to chance? Chen chose her words carefully. When we have direct evidence of intent. Until then, we follow the data wherever it leads, while remaining appropriately skeptical. And where's the data leading? She paused. Toward questions we're not used to asking. Behind the scenes, the debate was more intense. In a private email exchange between senior astronomers, one researcher wrote, "We need to stop dancing around this. The trajectory is anomalous. The chemistry is anomalous. The mass is anomalous. The Mars offset is anomalous. At some point, anomalous stops being a curiosity and starts being a pattern." Another responded, "Patterns can be coincidence. We need extraordinary evidence before we claim extraordinary conclusions." A third, "We have 7 distinct anomalies. How many does it take before extraordinary evidence becomes cumulative evidence?" The exchange was leaked to a science journalism blog on February 18th. It went viral within hours, because it crystallized the question everyone was asking, but few were willing to state directly, how much is too much? How many anomalies before you stop calling it natural? Avi Loeb didn't hesitate. In a new op-ed published February 20th, he laid it out plainly. "We now have a complete picture of 3I Atlas's trajectory. It arrived aligned with our ecliptic plane. It threaded past 4 planets during a single pass. It reached perihelion when Earth couldn't observe it. It shows course corrections inconsistent with random outgassing. It carries a mass suggesting hollow structure. It emits chemicals found only in industrial processes. It pulses with mechanical regularity. Each of these alone could be explained naturally, with generous assumptions and unlikely scenarios. Together they form a coherent picture of something designed to behave exactly as it's behaving. The natural explanation now requires more assumptions than the artificial one. Occam's razor, properly applied, points toward intent." The response was predictable. Critics called him reckless. Loeb is no longer doing science. He's advocating for a conclusion without proof. Supporters called him brave. Finally, someone willing to follow the evidence honestly. But everyone agreed on one thing. The Jupiter encounter would be decisive. If 3I Atlas passed Jupiter and continued on a purely gravitational trajectory, no adjustments, no precision maneuvers, then maybe all of this was coincidence. But if it changed course again, if it used Jupiter for a gravity assist with the kind of precision only spacecraft achieve, then the debate would be over. Because you can't thread 4 planetary encounters, align with the ecliptic, hide during perihelion, and execute a perfect Jupiter flyby by accident. Not with 1 in 3 million odds, not unless you're navigating. Dr. Yuki Tanaka said it best in a late-night conversation with colleagues. "We're 3 weeks away from knowing. Either this thing is the luckiest rock in the universe, or it's not a rock at all." She stared at the trajectory projection on her screen. "And I don't believe in luck anymore." The red line curved through space, past Jupiter, then outward toward the edge of the solar system. Perfectly calculated, perfectly timed, perfectly threaded. Like every spacecraft trajectory she'd ever seen. Except this one came from outside, and no one had admitted to building it. As February ended and March began, observatories around the world prepared for the Jupiter encounter. Every major telescope, every space agency, every institution with the capability to observe. All eyes on one object, all waiting for one moment, to see if the needle would thread one more time, or if the universe would finally offer a natural explanation that didn't require believing in miracles. The countdown had begun, and the answer was less than 3 weeks away. March 3rd, 2025. Dr. Sarah Chen stood in front of a conference room at the European Southern Observatory, a projected slide behind her showing 9 bullet points, 9 anomalies, 9 pieces of data that didn't quite fit. The room was filled with 30 of the world's leading astronomers, video conferencing in from 6 continents. This wasn't a public presentation. This was internal, private. A chance to speak freely without media scrutiny or public pressure. Chen had been tracking 3I Atlas since July. 8 months of observations, 8 months of data that kept getting stranger. And now, with the Jupiter encounter just 2 weeks away, she wanted to lay it all out. Everything. In one place. She clicked to the first slide. Anomaly 1. Periodic brightness variation. The graph showed the light curve, that perfect, repeating wave, rising and falling every 11.7 hours with mechanical precision. Natural comets tumble chaotically, Chen said. Their brightness varies, but irregularly. What we're seeing here is regularity that suggests either perfectly stable rotation, which is statistically unlikely for an interstellar object that's been traveling for millions of years, or something else maintaining that stability. She clicked to the next slide. Anomaly 2, industrial chemistry. The spectroscopic data, nickel tetracarbonyl, 4.6 grams per second, no iron. This compound doesn't form naturally in space. Every formation scenario we've proposed requires special conditions that violate what we know about planetary chemistry. The simplest explanation is industrial production, but we're not saying that publicly because it sounds absurd. A few uncomfortable shifts in the room, but no one disagreed. Next slide. Anomaly 3, mass inconsistency. Delgado's calculations, 33 billion tons, massive enough that outgassing couldn't move it. The object is venting 150 kilograms per second of gas. That should produce measurable acceleration. It doesn't, which means either the mass is much higher than size suggests, implying low density or hollow structure, or the outgassing is perfectly symmetrical, which is impossible for a rotating irregular body. Next slide. Anomaly 4, trajectory alignment. Fung's orbital analysis. The threading path past 4 planets. The ecliptic alignment. The timing. Combined probability, approximately 1 in 3 million. Not impossible, but improbable enough that we should ask whether this trajectory was designed rather than random. Someone in the video feed raised a hand. Dr. Linda Zhao from MIT. Sarah, you're stacking probabilities in a way that inflates significance. Each of these individually is explainable. Chen nodded. That's correct. Each one alone has a possible natural explanation. That's exactly my point. We're treating each anomaly in isolation, finding a way to explain it, and moving on. But we're not looking at the pattern. She clicked to the next slide. Anomaly 5, hidden perihelion. The solar conjunction, October 29th. 3 weeks of invisibility at the most critical moment. The object reached perihelion when Earth was on the exact opposite side of the Sun. If you were planning a maneuver you didn't want observed, this would be the optimal time. The trajectory shift we detected afterward, 0.003 degrees, is consistent with a controlled burn. Or asymmetric outgassing, Zhao countered. Which brings us to Anomaly 6. Next slide. The Mars images. Anomaly 6. Offset brightness distribution. The high-rise data, the coma's brightest region 50 kilometers from the nucleus. This is consistent with outgassing from a shell rather than a solid core. Combined with the mass calculation suggesting hollow structure, we have independent confirmation of the same geometric model. Next slide. Anomaly 7. Thermal uniformity. James Webb's infrared data, temperature. Distribution 2 even for a natural object. Comets have hot sides and cold sides. This one doesn't. The heat distribution suggests active thermal management, not passive radiation. Next slide. Anomaly 8, chemical ratio inversion. CO2 to H2O ratio of 8 to 1. This is backwards from every comet we've studied. It's consistent with a storage tank of compressed CO2 rather than natural ice composition. Final slide. Anomaly 9, radio silence. Chen paused here. This one was harder to discuss because the data was ambiguous. Multiple institutions monitored 3I Atlas during the Mars encounter. No results have been published. When asked, responses are evasive. Either nothing was detected and institutions don't want to legitimize the question by saying so, or something ambiguous was detected and they're still analyzing. She turned to face the room. 9 anomalies, each explainable in isolation, barely. Together they form a coherent picture of an object that doesn't behave like natural debris from another star system. What are you proposing? Someone asked. Chen took a breath. I'm proposing we stop treating each anomaly as a separate puzzle and start seeing them as parts of a whole. That we apply the same analytical framework we'd use for any other scientific question. When multiple independent observations point toward the same conclusion, that conclusion deserves serious consideration. Even if the conclusion is extraordinary? Especially then. The room erupted in debate. Some agreed. She's right. We're cherry-picking natural explanations and ignoring the pattern. Others pushed back. This is confirmation bias. We're seeing what we want to see. Dr. Zhao was firm. Extraordinary claims require extraordinary evidence. What you're describing is a collection of unlikely observations. That's not the same as proof of artificiality. Chen didn't back down. I'm not claiming proof. I'm claiming the probability has shifted, that we've reached the point where the artificial hypothesis is more parsimonious than the natural one. That's not how science works. Then how does it work? How many anomalies do we need before we're allowed to ask uncomfortable questions? The debate continued for 2 hours. By the end, nothing was resolved. But something had shifted. For the first time, senior researchers were discussing the possibility openly. Not in whispers, not in private emails, out loud. even if half the room thought it was absurd. The next day, Avi Loeb published a formal proposal. It was titled Framework for Assessment of Interstellar Objects of Potentially Artificial Origin, and it appeared on the Archive preprint server on March 4th. The paper proposed a systematic methodology. Any interstellar object would be evaluated on 10 criteria. Trajectory precision, does it pass near multiple targets with improbable accuracy? Spectroscopic anomalies, does it emit compounds inconsistent with natural chemistry? Structural anomalies, does it show geometric regularity or mass inconsistencies? Temporal patterns, does it display periodic behavior suggesting controlled rotation? Thermal signature, does heat distribution suggest active management? Radio emissions, does it transmit or respond to signals? Course corrections, does it maneuver in ways unexplained by outgassing? Trajectory origin, does it arrive from a specific stellar source rather than random interstellar space? Response to observation, does behavior change when actively monitored? Physical composition, does surface analysis reveal manufactured materials? Each criterion would be scored 0 to 10 based on how strongly observations deviated from natural expectations. Any object scoring above 50 total points would trigger mandatory coordinated international observation. Above 70 points would trigger consideration of close approach missions. Loeb scored 3I Atlas. Trajectory precision, 8 spectroscopic anomalies, 9 structural anomalies, 8 temporal patterns, 9 thermal signature, 7 radio emissions, 3 ambiguous data, no confirmation. Course corrections, 6 trajectory origin, 4 no specific source identified. Response to observation, 0 insufficient data. Physical composition, 5 unusual but not conclusive. Total, 59 points. According to his framework, 3I Atlas warranted coordinated international investigation as a potentially artificial object. The paper was downloaded over 1 million times in the first week. Reaction was immediate and polarized. Dr. Marcus Delgado endorsed it. Finally, a systematic approach. This is how we should be handling these discoveries, with rigorous methodology, not knee-jerk dismissal. Dr. Yuki Tanaka was more cautious but supportive. The framework has merit. Whether the specific scores for 3I Atlas are accurate is debatable, but the principle is sound. Critics were harsh. Loeb has created a pseudoscientific scoring system designed to validate his pre-existing beliefs. One astronomer tweeted, "This isn't methodology. It's advocacy dressed up as science. The criteria are subjective. The scoring is arbitrary. This would never pass peer review." Dr. Zhao published a rebuttal. The problem with Loeb's framework is that it treats absence of natural explanation as evidence of artificiality. But our ignorance is not data. Just because we can't explain something doesn't mean it's aliens. Loeb responded, "And just because something could theoretically be natural doesn't mean we should assume it is. Science requires considering all hypotheses and following evidence." The debate spilled into mainstream media. News outlets ran stories. Harvard scientist proposes alien object detection system. Should we treat interstellar visitors as potential alien probes? Astronomy community divided over how to handle mysterious objects. But while the public was captivated, the institutions that mattered were silent. NASA. No comment on Loeb's proposal. European Space Agency. No comment. International Astronomical Union. No statement. The silence was deafening, because implementing Loeb's framework would mean admitting the question was legitimate, that the possibility of artificial interstellar visitors deserved formal protocols, and no institution wanted to be the first to say that out loud. So they said nothing. And in saying nothing, they made a choice. The choice to wait, to observe passively, to let the object pass through our solar system without extraordinary effort to understand what it might be. Dr. Chen found this deeply frustrating. In a private conversation with Delgado, she vented, "We have the capability to investigate this properly. We could redirect space telescopes, we could coordinate observations, we could even fast-track a flyby mission if we mobilized resources. But no one wants to be wrong. If we treat this as potentially artificial and it turns out to be natural, we look foolish. So institutions are protecting their reputations instead of pursuing truth." "And if it is artificial?" Chen was quiet. "Then we're watching the most important event in human history and doing the bare minimum because we're afraid of looking stupid." Delgado nodded slowly. "Future generations are going to ask what we did. When an interstellar object with 9 anomalies passed through our solar system, how did we respond? And the answer will be, we debated it on Twitter and did nothing." The conversation haunted Chen, because she knew he was right. Meanwhile, independent researchers were taking the data seriously. A team at Caltech compiled a comprehensive database. Every measurement, every observation, every anomaly related to 3I Atlas. They made it publicly available. Within days, citizen scientists were analyzing it, running their own models, testing hypotheses. A retired aerospace engineer noticed something in the trajectory data that professional astronomers had overlooked. The course correction at perihelion, the 0.03 degree shift, wasn't random in direction. It was aimed. If you extended the post-perihelion trajectory forward and accounted for Jupiter's gravity, the path led to a specific region of the outer solar system. Not random, targeted. The engineer published his findings on a blog. 3I Atlas appears to be heading toward the heliopause in the direction of the Voyager 1 trajectory. Was it coincidence, or was the object heading toward the edge of the solar system, toward the boundary where solar wind meets interstellar space? Toward the exit. The analysis was picked up by science journalists, then mainstream media. Is the interstellar visitor heading home? The question captured public imagination. Because if 3I Atlas was navigating, if it had a destination, then it wasn't debris. It was a mission. Dr. Tanaka read the analysis carefully. The math was solid. The trajectory did point toward the heliopause, but correlation wasn't causation. The object could be heading that direction by pure chance. Still, it was another data point. Another piece of the pattern. She added it to her own compiled list. By mid-March, that list had grown to 12 anomalies. The original 9 plus targeted post-perihelion trajectory, absence of fragmentation. Most comets break apart under thermal stress. 3I Atlas remained intact. Lack of brightness surge at perihelion. Natural comets typically brighten dramatically. This one didn't. 12 unexplained observations. 12 pieces of a puzzle. And still, institutions remained silent. Still, no coordinated investigation was launched. Still, the official position was interesting but probably natural. Dr. Chen gave one final interview before the Jupiter encounter. The journalist asked directly, "Do you think 3I Atlas is artificial?" Chen chose her words carefully. "I think we're looking at an object that challenges our assumptions about what natural interstellar debris should look like. Whether that means it's artificial, I can't say. But I can say this. We're not investigating it as thoroughly as we should be, and that's a failure of our institutions. What would thorough investigation look like? Dedicated observation campaigns, radio monitoring by SETI with published results, coordination between space agencies, consideration of a fast response intercept mission, treating this as potentially the most significant astronomical event in human history rather than as an inconvenient anomaly we'd prefer to ignore. Why aren't we doing that?" Chen smiled sadly. "Because it's easier to call it a comet and move on." The interview aired on March 12th. It was viewed 15 million times in the first 48 hours. Because Chen had said what millions of people were thinking. That the institutions we trust to explore the universe were choosing comfort over curiosity. That we were letting something potentially extraordinary slip through our solar system without asking the hard questions. That future generations would judge us for our timidity. And that judgment wouldn't be kind. As March 15th approached, the date of Jupiter encounter, telescopes around the world prepared for one final observation. One last chance to see if the pattern continued, if the object would maneuver again with precision that couldn't be explained by natural processes, if the needle would thread one more time. Because if it did, then the pattern would be undeniable, and the refusal to see it would become impossible to defend. Dr. Delgado said it best in his final blog post before Jupiter. "We have 12 anomalies, 12 observations that don't fit the natural model without generous assumptions. If 3I Atlas executes a precision maneuver around Jupiter, we'll have 13. At some point, the weight of evidence becomes too heavy to ignore. At some point, refusing to consider alternatives isn't skepticism, it's denial, and we're very close to that point." He concluded, "In 3 days, we'll know. Either this is the most improbable natural object ever observed, or it's something else. And if it's something else, we'll have to answer a much harder question. Why were we so afraid to find out?" The countdown began. 72 hours until Jupiter. 72 hours until the pattern either broke or became impossible to dismiss. 72 hours until humanity would be forced to confront what it had been avoiding for 8 months. The possibility that we were not alone, and that we'd been watching evidence of that truth the entire time. While calling it a comet, the Jupiter encounter had come and gone. 3I Atlas had passed within 54 million kilometers of the gas giant on March 16th, moving at 67 kilometers per second. Too fast for capture, but close enough for gravitational influence. Every telescope available had watched, and what they saw was ambiguous. The trajectory bent, as expected from Jupiter's gravity, but the amount of deflection was slightly, very slightly, more than pure gravitational models predicted. 0.02 degrees more, barely measurable. Within the margin of error for some instruments, but present in multiple independent observations. Dr. Lisa Feng had run the numbers 100 times. "It's consistent with a small course correction," she'd reported. "Thrust of maybe 200 newtons applied for 3 hours during closest approach. but it could also be explained by outgassing asymmetry, or by Jupiter's gravity being slightly stronger than our models account for, or by measurement error. In other words, inconclusive. Not proof of maneuvering, but not proof it didn't maneuver, just ambiguous. The media had treated it as vindication of the natural hypothesis. Interstellar object passes Jupiter without anomalies, the headlines read. But in the scientific community, the debate intensified, because ambiguous meant the pattern hadn't broken. 13 anomalies now. The Jupiter deflection joined the list, and as March turned to April, as 3i Atlas moved beyond Jupiter and into the outer solar system, a different kind of conversation began. Not about what the object was, but about what it meant if it was artificial. Dr. Amara Okonkwo, the chemist from Caltech, was having coffee with a colleague, Dr. David Park, an astrobiologist, when the conversation turned philosophical. Let's just assume for a moment, Park said, that Loeb is right, that 3i Atlas is a probe. What does that imply? Okonkwo stirred her coffee. That we're not alone. Obviously, but think deeper. What kind of civilization sends a probe that looks like a comet, that hides in plain sight? A cautious one. Park nodded. Exactly. A cautious one. Which raises the question, what are they being cautious about? The question hung in the air. Over the next few days, Park couldn't stop thinking about it. He was familiar with the Drake equation, the famous formula for estimating the number of communicative civilizations in the galaxy. He'd spent years studying extremophiles, thinking about what life might look like on other worlds, but he'd never seriously considered the Fermi paradox from a darker angle. The paradox is simple. If intelligent life is common in the universe, where is everyone? Why don't we see evidence of civilizations everywhere we look? There are many proposed solutions. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations destroy themselves before becoming spacefaring. But there's another possibility, one that's harder to think about. The dark forest hypothesis. Park had read Liu Cixin's science fiction trilogy years ago. The central premise had always seemed like fiction, paranoid, pessimistic. But now, looking at 3i Atlas, he wasn't so sure. The dark forest hypothesis suggests the universe is full of civilizations, but they all stay hidden, because revealing yourself is dangerous. Here's the logic. You can't know the intentions of alien civilizations. They might be peaceful, but they might not be. You can't know their capabilities. They might be far more advanced than you. Given those uncertainties, the safest strategy is silence. Don't broadcast. Don't make yourself a target. And if you do detect another civilization, eliminate them before they can eliminate you. Strike first from a position of advantage. The result? A universe where everyone is hiding, everyone is watching, and everyone is ready to destroy anyone they find. A dark forest, where making noise means death. It's a grim scenario. Most astrobiologists reject it as overly pessimistic. But it provides one answer to the Fermi paradox. We don't see anyone because everyone who reveals themselves gets destroyed? And if that's true? What does it mean that 3i Atlas, if artificial, was designed to look natural? Park started writing, not a scientific paper, just notes, thoughts. If you're sending probes to other star systems and you subscribe to dark forest logic, you design them to be inconspicuous, coated in ice, venting gas, looking like natural debris. You'd gather information without revealing your presence. You'd survey without announcing yourself. He continued, a probe that screams, I'm artificial, is a probe that invites response. Maybe hostile, but a probe that looks like a comet, that just passes through, unnoticed, unremarked? That's perfect reconnaissance. He paused, staring at what he'd written. Because there was a darker implication. Reconnaissance comes before action. You don't scout a system unless you're planning something. Maybe it's benign, scientific curiosity, first contact preparation. Or maybe it's not. Maybe you're gathering data for future exploitation, resource assessment, threat evaluation. Maybe you're deciding whether this system is worth claiming, or whether the civilization here needs to be neutralized. Park felt a chill. He was speculating wildly now, he knew. Building castles of paranoia on a foundation of ambiguous data. But the thought wouldn't leave him. What if 3i Atlas wasn't first contact? What if it was reconnaissance before conquest? He deleted the notes. Too dark, too speculative. But the questions remained. A few days later, he mentioned the idea to Okonkwo. Her response surprised him. I've been thinking the same thing. Really? Not conquest, necessarily, but why does a probe need to be stealthy? The only reason is if you don't want to be noticed. And the only reason you don't want to be noticed is if revealing yourself carries risk. Risk to whom? To you. To us? To both. Park leaned forward. Explain. Okonkwo thought for a moment. If you're an advanced civilization and you detect another civilization, you have choices. Contact openly, observe discreetly, or eliminate the potential threat. Dark forest. Exactly, but here's the thing. Maybe civilizations that survive long enough to become interstellar have learned to be cautious. They don't make first contact loudly. They scout first. They assess. They watch. And then? And then they decide. Is this species worth talking to? Worth trading with? Worth ignoring? Or worth eliminating? Okonkwo nodded slowly. That's the nightmare scenario, yes. The conversation stayed with both of them, and they weren't alone in thinking it. Across the astrobiology community, similar discussions were happening, in emails, in video calls, in late-night conversations. Because 3i Atlas, if artificial, raised uncomfortable questions about intent. Why survey the inner solar system? Why pass near Earth, Mars, Venus, Jupiter? Why maintain the appearance of a comet? What information was being gathered, and what would be done with that information? Dr. Sarah Chen found herself in one such conversation in mid-April. A colleague asked her directly, "If it's a probe, do you think it's friendly?" Chen didn't know how to answer. I think assigning friendly or hostile to an object we don't understand is premature. But if you had to guess, Chen was quiet for a long time. I think, if a civilization is advanced enough for interstellar travel, they're probably beyond the need for conquest. Resources are abundant in space. Why fight over planets when asteroids and comets provide everything you need? So, friendly? Or indifferent? Maybe we're just insects to them. Interesting, but not threatening. Not worth engaging. That's not comforting. No, Chen admitted, it's not. Because indifference carried its own implications. If an advanced civilization viewed humanity as we view ants, curious, observable, but ultimately irrelevant, then our concerns, our fears, our hopes wouldn't matter to them. We'd be studied, cataloged, noted, and then forgotten. The conversation turned to what humanity should do if 3i Atlas were confirmed as artificial. Should we try to communicate? Someone asked. With what? It's leaving. It's already beyond Jupiter. By May, it'll be too far for any signal to catch up. So we just watch it go? Unless someone wants to fund an intercept mission? The idea had been proposed. A fast launch probe, using nuclear propulsion or solar sails, racing to catch up with 3i Atlas before it left the solar system. The engineering was theoretically possible. Difficult, expensive, but possible. But it would require international cooperation. Billions of dollars, years of development, and most importantly, consensus that it was worth doing. That consensus didn't exist. NASA's position: interesting object, but missions require extensive planning and justification. ESA's position: we're monitoring the situation. China's position: no public statement, private space companies, intrigued but not committed. So the idea languished, and the 3i Atlas continued its journey outward, receding at 67 kilometers per second. By late April, it was beyond effective observation range for most telescopes, still visible, barely, to the largest instruments, but too faint for detailed study. The window was closing. Dr. Marcus Delgado wrote a final blog post on April 28th. We are watching 3i Atlas fade from view. In a few weeks, it will be too dim to track. In a few months, it will be beyond the orbit of Saturn. In a few years, it will cross the heliopause and return to interstellar space. And we will never know for certain what it was. We will have data, mountains of it. Observations, measurements, spectra, trajectories. We will have debates that continue for decades. We will have believers and skeptics, each armed with their interpretation of ambiguous evidence. But we will not have certainty. Because we chose caution over curiosity. We chose institutional reputation over scientific truth. We chose to call it a comet and move on, rather than confront the uncomfortable possibility that we were looking at something extraordinary. Future generations will judge us for that choice, and they will be right to do so. The post went viral, over 10 million views, thousands of comments. Some agreed, we had one chance and we blew it. Others disagreed, we followed the evidence, it was inconclusive. Moving on is appropriate. But everyone felt the weight of the moment. Because whether 3i Atlas was natural or artificial, it represented a lost opportunity. An opportunity to investigate thoroughly, to answer definitively, to know rather than speculate. And that opportunity was gone. Dr. Yuki Tanaka had the last word in a radio interview on April 30th. The saddest part, she said, is that we'll never be able to tell our grandchildren what it was. We can only tell them what we think it might have been. And that uncertainty, that permanent, unresolvable uncertainty, is the price we pay for timidity. The interviewer asked, "Do you think it was artificial?" Tanaka was quiet for a long moment. "I think we saw something we weren't ready to see. Something that challenged our assumptions about our place in the universe. And instead of rising to that challenge, we retreated into comfortable explanations." That's not an answer. No, Tanaka agreed. But it's the truth. As April ended and May began, 3. Atlas continued its silent journey into the outer solar system. The telescopes stopped tracking it, the papers stopped being published. The news cycle moved on. The object that had captivated the world for 10 months faded from public consciousness, but not from the minds of those who'd studied it. Dr. Chen kept a folder on her computer. Every measurement, every observation, every anomaly, 13 in total. 13 pieces of a pattern she couldn't unsee. Late at night, when she couldn't sleep, she'd open the folder and review the data. The pulse, the chemistry, the mass, the trajectory, the timing, every piece explainable alone. Together, a picture. A picture of something that looked exactly like what you'd design if you wanted to survey a solar system without being noticed. A probe coated in ice, venting gas like a comet, threading past planets with precision, gathering data, and leaving. Returning to the darkness with whatever it learned. Chen would close the folder and stare at the ceiling, and ask herself the question she couldn't answer. Did we just watch something leave? Or did we just miss the most important discovery in human history because we were too afraid to admit what we were seeing? The question haunted her, as it haunted Delgado, and Tanaka, and Feng, and Loeb, and thousands of others who'd followed the story. Because deep down they all knew. The data didn't prove artificiality, but it didn't prove nature either. It sat in uncomfortable ambiguity. And in that ambiguity lived a possibility. A possibility that somewhere out there, beyond the orbit of Saturn, beyond the heliopause, beyond the edge of our solar system, something was carrying information about us, about our world, our civilization, our capabilities, back to wherever it came from, back to whoever sent it, and we would never know what they would do with that information. Never know if the next visitor would be as subtle, or if it would be something else entirely. The dark forest whispered its warning, and humanity, having glimpsed the possibility, turned away, choosing the comfort of uncertainty over the risk of truth. As 3i Atlas disappeared into the night, the lights of human civilization continued to shine, broadcasting our presence to anyone watching, unaware or unwilling to accept that someone might be, and that they might not be friendly. The forest remained dark, and the silence continued, louder than any signal could ever be. October 15th, 2025. Dr. Sarah Chen sat in her office at the European Southern Observatory, watching the sunset over the Chilean desert. The sky was turning that particular shade of purple that only exists at high altitude, far from city lights. In a few hours, the telescopes would wake up, the domes would open, the instruments would begin their nightly routine of photographing the universe. But tonight they wouldn't be pointed at 3i Atlas, because 3i Atlas was gone. Not destroyed, not disappeared, just too faint. Beyond the orbit of Saturn now, racing outward at 67 kilometers per second, the object had faded to magnitude 24, barely visible even to the most powerful telescopes on Earth. The last confirmed observation had been September 12th, using the European Southern Observatory's Very Large Telescope. A single pixel of light against the background stars, moving, fading, and then nothing. The object that had dominated her life for 15 months had slipped beyond reach. Chen pulled up a folder on her computer. Inside were 847 files. Spectra, light curves, orbital calculations, mass estimates, temperature measurements, 15 months of data, and still no consensus on what it meant. She opened a document she'd been working on for weeks, a comprehensive analysis. Everything in one place. The title, High Toroidal 3 Atlas, a retrospective analysis of anomalous characteristics in an interstellar visitor. She'd submitted it to the Astrophysical Journal 3 days ago. The reviewer's comments had come back this morning. Reviewer 1, thorough compilation of observations. However, the author's interpretation leans too heavily toward artificial origin without sufficient evidence. Recommend major revisions to maintain neutrality. Reviewer 2, while the data is compelling, the conclusion that 3i Atlas represents a non-natural object is not supported. Each anomaly has plausible natural explanations. Recommend rejection. Reviewer 3, important work documenting unusual characteristics. However, framing this as possibly artificial will damage the credibility of serious astronomy. Suggest rewriting to focus on natural formation scenarios that could explain observations. Chen read the comments twice, then she closed the document. They wanted her to change the conclusion, to soften it, to pretend she didn't see what she saw, to call it a comet and move on. She understood why. The scientific community had a reputation to protect. You don't get funding by claiming to study alien probes. You don't get tenure by being the person who cried aliens over ambiguous data. But she also understood something else, that sometimes protecting reputation means sacrificing truth. She opened a blank document and started writing. Not a revised paper, not a softened conclusion, a letter. To future astronomers, by the time you read this, 3I Atlas will be long gone, a memory, a footnote in the history of interstellar object discoveries. But I want you to know what we saw, not the sanitized version, not the careful, reputation-protecting version. The truth. We saw an object that pulsed with mechanical regularity, that emitted industrial chemicals, that threaded past 4 planets with precision that looked navigated, that maneuvered behind the sun when we couldn't watch, that showed mass inconsistencies suggesting hollow structure, that passed Mars with brightness distributions inconsistent with solid comets, that bent around Jupiter with trajectory changes that might have been intentional. We saw 13 anomalies, and we called it a comet, because calling it anything else was too uncomfortable. I don't know what 3I Atlas was. I wish I did. But I know what we did wrong. We treated each anomaly in isolation. We found natural explanations that required unlikely assumptions and called that sufficient. We refused to look at the pattern because the pattern implied something we weren't ready to accept. If you encounter something similar, and you will because the universe is large and we're detecting more interstellar objects every year, please learn from our mistake. Don't be afraid to ask uncomfortable questions. Don't let institutional caution override scientific curiosity. Don't let the fear of being wrong prevent you from investigating thoroughly. Because if 3I Atlas was natural, we wasted some telescope time. But if it was artificial, we missed the most important discovery in human history. And we'll never know which. That uncertainty is our legacy. Don't let it be yours. Dr. Sarah Chen, October 2025. She saved the letter in the same folder as all the data. 15 months of observations. 1 letter to the future. Then she closed her laptop and walked to the window. Outside, the desert was darkening. Stars were appearing. Somewhere up there, 3I Atlas was still moving, carrying whatever truths it held into the void. Across the world, in dozens of institutions, similar moments were unfolding. Dr. Marcus Delgado had archived his calculations, the mass estimates, the trajectory analysis, the probability calculations. He'd written a final blog post titled, "What We Learned from 3I Atlas." It wasn't about the object itself, it was about the response. We learned that our institutions are not prepared for ambiguous discoveries. We have protocols for clear threats, asteroids on collision courses. We have protocols for clear opportunities, new planets to study. But for something in between, something that might be extraordinary or might be ordinary, we have nothing. We debated instead of investigating. We speculated instead of observing. We protected our reputations instead of pursuing truth. 3I Atlas deserved better. Science deserves better. And the next time, and there will be a next time, we need to do better. The post was shared 50,000 times, but no institution changed its policies. No new protocols were established. No international framework for investigating potentially artificial objects was created. The system that had failed 3I Atlas remained unchanged. Dr. Yuki Tanaka had stopped giving interviews in August. She was tired of saying the same things, tired of defending data that spoke for itself, tired of watching people choose comfort over curiosity. But she kept watching the sky, because she knew something that most people didn't want to acknowledge. 3I Atlas wasn't unique. The Vera Rubin Observatory, fully operational as of early 2025, was discovering interstellar objects at an accelerating rate. 3 had been confirmed since August, all smaller than 3I Atlas, all clearly natural, all unremarkable. But the discovery rate was increasing. 1 every few months now. Soon it would be 1 per month, then 1 per week. The solar system was busier than anyone had realized, and statistically, if technological civilizations existed anywhere in the galaxy, if they sent probes, eventually we'd encounter one. Maybe we already had. Tanaka had created a database, every interstellar object detected, every observation, every anomaly. She was looking for patterns, because if 3I Atlas was artificial, it probably wasn't alone. There would be others. And if you looked at enough objects, patterns would emerge. She hadn't found them yet, but she was looking. Because someone had to. Avi Loeb had taken a different approach. In June, he'd founded an organization, the Interstellar Object Research Initiative, privately funded, independent of major institutions. Its mission, systematic investigation of interstellar visitors using the framework he'd proposed. Within 3 months, they'd raised $12 million from donors who believed the question mattered. They'd secured telescope time, hired researchers, built a rapid response observation network. When the next unusual object appeared, they'd be ready. Not with institutional caution, not with reputation protection, with full-throated scientific investigation. Loeb knew he was controversial. He knew half the astronomy community thought he was chasing fantasies. But he also knew he was right about one thing. The question deserved to be asked. And if institutions wouldn't ask it, someone else had to. By late October, the media had moved on. 3i Atlas was old news. The speculation had faded. The headlines had stopped. But in certain corners of the internet, the discussion continued. Forums dedicated to the object remained active. YouTube channels still analyzed the data. Reddit threads still debated the anomalies. Because for millions of people, 3i Atlas had represented something important. Not just a comet, not just an astronomical curiosity, a possibility. The possibility that we weren't alone, that the universe contained other minds, other civilizations, other travelers, and that possibility, once glimpsed, was hard to forget. Dr. Amara Okonkwo had returned to her regular work, studying astrobiology, analyzing meteorites, thinking about the chemistry of life, but she kept a file on her desktop. 3i Atlas Chemistry. Inside were all her analyses, the nickel tetracarbonyl detection, the CO2 ratios, the spectroscopic anomalies. She opened it sometimes, late at night, and stared at the data. The compound that shouldn't exist in nature, but did. Coming from an object that looked exactly like what you'd design if you wanted to survey a solar system without being noticed. She didn't talk about it anymore, didn't publish about it, didn't speculate publicly, but she thought about it. Every time she looked up at the stars. In November, a science journalist published a long-form article, "The Comet We'll Never Forget, What 3i Atlas Taught Us About Ourselves." It wasn't about the object. It was about the response, about how humanity reacts when confronted with the unknown, about how institutions choose safety over discovery, about how the fear of being wrong can prevent us from being right. The article concluded, 3i Atlas is gone now, fading into the darkness between stars. We'll never know for certain what it was, natural or artificial, debris or design, random or intentional. But we know what we did. We watched the most unusual interstellar object ever detected pass through our solar system, displaying anomaly after anomaly, and we chose not to investigate thoroughly. We chose caution, reputation, comfort, and in doing so we may have missed the most important discovery in human history, or we may have correctly identified an unusual but natural object and moved on appropriately. We'll never know. And that uncertainty, that permanent, unresolvable uncertainty, is our legacy. The next time an unusual visitor arrives, we'll face the same choice. Will we choose differently? Or will we let another opportunity slip away because we're afraid of what we might find? The article was read by 5 million people, and nothing changed, because changing would require admitting we got it wrong, and institutions don't like admitting that. As 2025 drew to a close, astronomers around the world continued their work, photographing galaxies, studying exoplanets, measuring cosmic expansion, but in the back of their minds, many of them carried a question. What if? What if 3i Atlas was artificial? What if we watched a probe from another civilization pass through our solar system and dismissed it as a comet? What if the data we ignored was the most important data we'd ever gathered? What if we were being observed, studied, cataloged? And what if, somewhere out there in a star system we couldn't name, beings we couldn't imagine were reviewing the data their probe had gathered, learning about us, our world, our capabilities, deciding what to do next? The questions had no answers, only possibilities, and the waiting. Dr. Chen stood at the window of her office, watching the stars emerge. 3i Atlas was out there somewhere, beyond Saturn, beyond the heliopause soon, returning to the interstellar void, carrying its secrets. She thought about the letter she'd written, the data she'd compiled, the truth she'd tried to preserve. Future astronomers would study this case. They'd analyze what we saw and how we responded. They'd judge us. And she hoped, desperately hoped, that when the next unusual object appeared, they'd do better. That they'd learn from our caution. That they'd ask the uncomfortable questions. That they'd investigate thoroughly, courageously, honestly. Because 3i Atlas wouldn't be the last. The universe was too vast. The number of stars too great. The possibility of other civilizations too real. Eventually, another visitor would arrive. One that couldn't be explained away. One that forced the question we'd avoided. Are we alone? And when that moment came, humanity would have to answer. Not with speculation, not with debate, with action. With the courage to confront what we found, even if what we found changed everything. Chen turned away from the window. Outside, the telescopes were opening. The night's observations beginning. Somewhere in the data they'd gather tonight, or tomorrow, or next week, might be another speck of light. Another visitor, another chance. And this time maybe we'd be ready. Or maybe we'd make the same mistakes. Choose the same caution. Miss the same opportunity. Only time would tell. But one thing was certain, the waiting would continue, because the universe was patient, and eventually it would send us something we couldn't ignore, something that would force us to see what we'd been refusing to look at, the truth that we were not alone, that we had never been alone, that the silence we heard was not absence, but waiting, just like us, for the moment when everything would change. That moment hadn't come yet, but it would. And when it did, the data from 3I Atlas, the comet that might not have been a comet, would matter. Because we'd finally understand what we'd been looking at, and why we'd been too afraid to see it. The stars continued their ancient dance, and humanity continued watching, waiting for the next visitor, the next anomaly, the next chance to get it right, or to fail again. The choice, as always, would be ours.